Let's get started. So today, we're very lucky to have Stella Offner. He was a professor at UT Austin. Stella did her PhD at UC Berkeley under the guidance of Chris McKee. She then came here to the ITC, so it's really great to have her back. She was a NSF fellow here, working with Alyssa in the ITC, and then moved on to Yale as a Hubble fellow, working with Hector Arce, and then became a professor at UMass Amherst until she went
until I wasn't.
Until she wasn't, and is now at UT Austin. Stella is an expert on all things star formation, astrochemistry, machine learning, numerical simulation. So I think we'll be getting a very interesting today. So thank you.
Great, thanks, Anna. So today I'm going to be talking about harnessing machine learning to study stellar feedback. So why would we want yet another tool to study star formation, particularly machine learning? And the answer is really because star formation is so messy, right? So here's what I mean, right? So star formation begins on the galactic scale, right? And it happens in giant molecular clouds, but they inherit their environment from the larger galactic environment, right? So their velocity dispersion, magnetic field structure, and their formation depends upon their surroundings. And then within molecular clouds, right, an individual star system forms within a dense core, and it too, it really depends upon its environment within the cloud, and that environment sets its turbulence, its rotation, the magnetic pressure support that might be within the core. And finally, on the smallest scales, you would think by the time we get to a few to 100 AU, that it would be independent of the broader context. But it turns out even the accretion disk depends upon the rate in which material is fed down from the core, right? So it depends again on the core properties, turbulence, and rotation. It's really setting the regulation of material from the disk onto the star. So this is messy because you have a very coupled problem that spans at least 7 orders of magnitude in spatial scales, and you have these interconnected physical processes, magnetic fields and gravity and turbulence that span many orders of magnitude. So all those processes basically are carrying mass, momentum, and energy from the largest scales all the way down to the small scales. But unfortunately, you're not done there, right? Because there's stellar feedback that starts on sub-AU scales and then acts to bring mass, momentum, and energy from the smallest back to the larger scales. So you have protostellar outflows from young stars. You have stellar winds and radiation, ionization from more massive stars. And finally, for the most massive stars, they really drive the process of ending star formation in the local environment and sweeping up and returning all of that material back into the galactic ISM. So altogether, you basically have what is essentially a cycle of life. So I admit I looked to replace this with the new Lion King pictures, but I just didn't like them as much. Like, this is very classic. So to summarize this messiness, right, we start with some properties within a molecular cloud as it's being formed, a bunch of completely nonlinear and interconnected and confusing things happen, and somehow at the very end of this process, you have a star or star cluster. So my goal as a theorist is to really replace this with this. So we have a more controlled numerical experiment where we can put in different ingredients and then look to see what the impact is on the broader star formation picture. So the simulations I'm going to be talking about today are carried out with the Orion code. So Orion is an adaptive mesh refinement code, which basically allows you to concentrate high resolution in regions of interest. You can resolve on density, velocity, or magnetic gradients, and thus really resolve the star formation on very small scales very well. And then you can make this efficient by not having to resolve the broader scales at the same resolution. So this code, of course, follows supersonic turbulence, gravity, radiation, including ionization and direct radiation, which Anna works on, magnetic fields, star particles. So the stars accrete, radiate, and launch stellar feedback. So the driving question behind my work is really, how does feedback shape clouds and star formation? So this is really what I'm hoping to use machine learning to try to address. All right, so what am I going to be talking about today? So I'm mainly going to be focusing on stellar winds or wind bubbles. So why? And then I'm going to tell you about 3 approaches to finding stellar wind bubbles: humans, by eye, and 2 machine learning approaches. I'm going to summarize some takeaway lessons from feedback identification, including what we can learn about the mass, momentum, and energy of feedback interactions. I'm going to tell you why human searches are flawed. You know some examples, but in particular. And then we're going to weigh turbulence versus feedback. All right, so I first became interested in stellar winds back when I was a postdoc and I arrived here and began working with Alyssa. And they had found this rather curious result. They looked at Perseus and they mapped out all the outflows and shells within the cloud. And they found that, amazingly, that these wind-driven bubbles, probably driven by B-type stars, basically comprised a huge amount of the total momentum and energy within the cloud, particularly if you added them up, some 50% of the cloud's turbulent energy. All right, so this is fairly surprising because Perseus is not a massive star-forming region. Right, so what's going on here? This was followed by work in Taurus, and they again looked at the molecular data and identified some 37 shells here, making up something like 30% of the cloud's turbulent energy. And so this was even more perplexing because Taurus not only does not have any O stars, it also doesn't have any B stars. So how are you getting these features, and what exactly is going on within these clouds? So one of the main points was that the feedback from outflows and winds was so significant that it was able to replenish, even in this relatively wimpy star-forming region, the local turbulence. So I tried to understand this using turbulence simulations, including feedback sources. And you won't see much of the turbulence here, but you can see the winds expanding, but that's okay.
The mesh says I should turn the lights
Yeah. No, that's good. No, it's okay. This is the only really dark slide. All right. So given that we have these simulations, the answer, one of the things that I wanted to answer was, is this feedback really doing anything? Can it act globally? Can it really, on global scales of the cloud, offset turbulence? Or is this merely a kind of local process where these stars and shells are just interacting with their immediate surroundings? Yes, they're dumping in a lot of energy locally, but maybe that doesn't have a big effect on the broader scale. So the nice thing about simulations is that we know exactly where the feedback is, and we can really constrain what it's doing. So one thing we did was to basically try to constrain what the feedback was doing locally versus globally. So it turns out that in magnetized clouds, as the feedback expands, as shells expand, right, they can kind of pluck on the magnetic field and excite magnetic waves, which propagate ahead of the actual feedback shell boundary. So we were able to isolate this effect. So here's velocity dispersion with all of the gas, and then you have subtracting out where the feedback is, and then comparing it to a simulation that's the same, but with no feedback at all. And you see there's a signal of maybe some 30% difference, where you're getting this excess energy injection, this basically action at a distance, which is injecting energy into the cloud, but not in a way that's easily observable. If you do this with smooth calculations with no turbulence, you can see the waves propagating ahead of the shell, but trying to see this in a turbulent environment is not so clear. So this helped to convince me that not only was there a lot of energy in the shells themselves, but this could potentially be a global effect, right? where these shells can reach larger scales beyond their immediate environment. So they also seem to flatten the power spectrum, and they create a kind of stirring. So they're changing the turbulent properties, right? It gets slightly more stirring to compression. So the other avenue that we can try to understand is, well, maybe we should just check all these shells. Are they really real shells? Maybe we're overcounting because we're seeing features that aren't actually produced by these stars, and so maybe this is inflating what the feedback is doing, particularly in a region like Taurus, right, where there aren't massive stars. So to do this, to really get at this issue, we need to work on new approaches to find and measure the feedback. So this is one of my favorite images of feedback. This is the Spitzer Galactic Plane Survey. And it's in dust emission. You can see the warm and hot gas, right, in yellow and red. And what you can see is that feedback is everywhere. These shells are everywhere throughout the entire galactic plane, right? Not just in star-forming regions, but really shaping the ISM itself. And so these are made, you can pick them out pretty easily here in this one segment, probably produced by O and B type stars or maybe star clusters, right, where they're sweeping up, heating and ionizing the gas around them. Right, so on the galactic scale, when you're not just looking at a particular region, there's a huge amount of data. So what I showed you was something like 1/8 of the galactic plane. So astronomers are very busy, right? So, which is one reason why we want to automate searches. But the other thing that we can do is we can get volunteers, right? So this is a citizen science project where they reached out to the general public, the Milky Way project, and they basically had people look at images of the galactic plane data and go ahead and classify and identify features. So for example, they would see an image something like this. They'd say, is that a shell? Is there a shell in this image? They would say yes, and then they would draw a little circle. So that would help you constrain, for example, the size of the shell and maybe the rate of feedback injection. However, you might see something like this. Is it a shell? Not totally clear, right? So we don't really know. Okay. So human identifications have some pros and cons, right? So pro, we engage the public in science, which is extremely important these days, more so than ever. The public is extremely numerous, right? They are way more numerous than professional astronomers. So that's a huge untapped potential. They work for free, unlike graduate students. So it gets better and better. And contrary to what you might think, humans are smart. So if you give a human an image with something weird in it, they will tell you about it. And in fact, many of these citizen science projects have kind of chat areas where people can say, hey, in this particular image, I saw something interesting, maybe we should follow it up, right? So this was actually how quasar light echoes were discovered initially. Now, on the minus side, humans need pretty simple instructions, right? So everybody's working from the same rubric. They can have different opinions. Ask 10 different people. You can get a range of different opinions about where the feedback is or whether it is feedback or not. And they can be hangry, right? Depending upon whether they had breakfast that morning, an image may or may not look like it contains feedback, right? So there's some optimism and pessimism and grumpiness that goes on. And of course, the real problem with human identification is that even the experts don't know the right answer. And Abby's not here, but I hear I'm being recorded, so he can watch it later. Yeah, so this is a big problem, particularly with these galactic plane surveys, is even expert astronomers can have differences about where the feedback is or whether or not something is feedback. And we really have no way of independently saying whether they're right or not. But this is where simulations and synthetic observations come in, right? Because here we put in the feedback, we can track it, we know exactly where the feedback is, right? And so we also know where it is not. So we can use this for training. So we can post-process the simulations with radiative transfer. observe them as if they're real starfing regions or bubbles, and then produce a set of images where we know definitively the things in the image are actually feedback. So this sets up a very nice training set. So now that we have this training set, we can do two things. One, we can use it to test humans. We can feed it back into the Milky Way project and actually see how people do. The other thing we can do is develop a new method, an automated method, using machine learning. Now, this seems pretty scary, like maybe the machines are coming for your jobs. So maybe not quite yet, but just to make you feel a little bit better, I'll replace it with this image so you're feeling a little bit more comfortable about the machines. This is definitely a very friendly one. So, all right, so now we can develop some kind of algorithms using this training set, which we understand completely. So for the first project, we used an algorithm that was developed actually here at the CFA by one of the Harvard grad students, Chris Beaumont. So this was a random forest approach. And Chris actually developed this and trained it initially using the real data, right? So the idea was, okay, well, we're going to use the real data. We still may not know the right answer, but it will be a lot faster than humans if we can get it to work correctly. So in this method, so basically it's a decision tree. So the algorithm is looking for features in the data, which are usually determined in part by the people who are setting up the training. So for example, if you apply this to animals, you'd say, right, we have an image. How many tails does it have? Right, if it has more than one tail, it can't be a cat. Right, if it has more than two legs, it probably is a cat. Right, and so by the end of the diagram, we've identified some image as either being a cat, right, or not a cat. So this same approach can be applied to observational and astronomical data. And we wanted to basically see if we can improve the algorithm by giving it our training set instead of real data. So we tried to make our training set as accurate as possible, right? So we carried out synthetic dust observations. We were very particular about the dust model. It had to include PAHs so that the spectra would essentially match what we know about the observed regions. We make sure we have a range of different times, magnetic field strength, star properties, viewing angles, with and without noise, centered, not centered, and then we tested it with and without observational data included in the training set. Yes? Yeah, that's a good question. So the other thing which you picked up, which I did not put here, is we also took the real data off feedback features and added it as foreground or background emission. So there was some nebulosity within the images, right, that was including, for example, background stars and things like that. Yeah. So that was key too. All right. So at the end of talks, if not in the middle, I usually get the question of, well, that's very nice, but are your simulations actually realistic? All right, and I think that the best way to answer that question is to basically see, does the machine learning algorithm, can it be trained only on simulations and then identify real observational feedback features? All right, so let's see. So here is a number of bubbles. These were identified by people. Now, there's a range of confidence of these bubbles. So some of them are more strongly identified as bubbles, some of them less so. And then here's the machine confidence for Brute, the machine learning algorithm we're using. So again, this is human identified features. And this red line here denotes the difference between things that we're going to go ahead and say, all right, it's definitely a bubble versus not a bubble. You have to pick some confidence level. So here's the original result, trained only on observational data and then tested on observational data. Now what if we, so that's pretty good, but what if we train it only on these synthetic observations? We can actually improve the detection of bubbles here. So we're pushing it to the right to higher confidence. So what is actually going on here? It's worth breaking this down. So there's really two changes in this curve. These things here have been moved to the right to higher confidence. And what's getting moved to the right are more yellow bubbles, which are smaller, often harder to pick out, probably produced by lower mass stars. There's more nebulosity. And so these are things that would be harder to find by humans and harder to classify. But this is what we're actually modeling, so having these in the training set is a good thing, and this is what's being improved. On the other side, you can see that the red line is actually moved a little to the left. Some things are actually less confident bubbles, and which ones those are also makes some sense. The ones that are very clearly bubbles, but are not what I'm simulating, are things that have been moved to lower confidence. So again, this makes a lot of sense. I'm not modeling O-type stars, so we're able to improve the confidence of these features created by lower mass stars, which are much more abundant, but we're doing less well on these types of bubbles. In the end, we kind of settled for a compromise where we had about half simulation, making sure we're doing a little bit better on these yellow type features. And then we're also including observed bubbles, which gets us these O-type stars. So this was our best training. But ultimately, what this out, yes? Yeah, so there in the top line. So here we have kind of a mix of training sets where we have some synthetic and then slightly less Milky Way project bubbles. And this did worse, I think, because what this really shows you have to be careful about your training set, and that if you're picking only a small sample of some type of images, then your results are going to be somewhat skewed as well. So, yeah. So I think probably in this case, we had probably not enough of the massive bubbles. We are maybe overpopulating certain types of things, and that's what was going on. Yeah. All right. So the things that we found as a result of this augmented training set were more features created by lower mass stars, particularly these yellow bubbles, which are hard to identify. So I think what we've shown is that machine learning and simulations can help improve data identification, right? So machine learning is great because it's repeatable. Every time you run it, you get the same answer. It's fast. It can run in minutes, right? It can't be hangry, right? So there's never any attitude. But you have to be really careful. You have to really know your training set. You have to really know your data and make sure you're not introducing any kind of biases when you're setting up your training set, right? So that's really important. Okay. So star formation is messy, but it's also three-dimensional, right? And this is where the human visual identification problem gets harder. So this is a movie, courtesy of Alyssa, right, the B5 part of Perseus. And it's basically a CO spectral cube. So it's a 3D data set. And if you look at it in the full 3 dimensions, position, velocity, you can really begin to see the structure of the cloud. Now, as part of their work in 2011, what they did is identified in this 3-dimensional space all of the feedback bubbles, right? So this was done by a particularly intelligent human, Michelle Borkin, who just happened to be especially qualified, right? Because her thesis was specifically on data visualization. So not a random member of the public trying to identify these shells. So, all right, so we want to create an algorithm that will do what Michelle does, but much faster and hopefully more accurately. So to do that, we need an even more intelligent machine learning algorithm. So we need convolutional neural networks. So these are sometimes called deep learning. The idea is that the neural network is reproducing what the human visual cortex does, right? So like before, it's supervised learning, right? So let's suppose we have an image. Let's call it a cat. So why is this a cat? Right? You guys can easily identify it's a cat, but why? It is my cat. You know it's my cat. Yes. That's outside information. It has a tail, right?
Exhibits topological cat features.
It exhibits the topological cat features, right, or characteristics. Yeah. This one's a hard example because it's a white cat on a white background, right? So your brain is really good at this. So if you look at this, right, this also has some topological cat features in the sense that it has an eye and a tail, right, but it's clearly not a cat. But if you look at this one, which is missing some of those features, you won't see the tail anymore. It is still a cat, even though it's a completely different color, right? So why is your brain so good at identifying cats? Right, and the answer is because since you were a small child, you've been building up a training set of cats, right? And your brain has basically learned the features of catness, right? But what your brain is not doing is really picking out those high-level features that you just told me about, but it's really breaking the image into a set of very small-scale features or filters, right? So picking up very small-scale parts of the image that are essentially cat-like. So the algorithm we developed is called the convolutional approach to shell identification. This slide is mostly for people who work on machine learning, right? So the rest of you can kind of tune it out. But this is a UNet architecture. We have 3 convolutional layers. We're using the mean squared error basically to train it and assess accuracy. We iterate for about 2,000 epochs, and then we converge to something like a few percent, right? So on the training set, we converge to very high precision. And then in order to complete the training, we have 1/3 training, 1/3 testing, assessing hyperparameters, and then 1/3 serves as a validation set, images it's never seen before that we can use to assess how well it's doing, right? The other main thing is that this is public and online, so you're welcome to download it and try it for yourself. Okay, so for our training set in this case, we want 3-dimensional data. So we tested it on 2 different things. One pure gas density, position, 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 and one on synthetic CO emission, so position, position, velocity. Again, we have different times, magnetic field strengths, star properties with and without noise, and we're actually working on 256 cubed spectral cubes. All right, so this is how it works. So here's our input, and in the training set, we're using our tracer field, which tracks the wind, as a target for what it's trying to learn, right? So after training, it identifies the appropriate filters and then gives back a prediction, right, which gives us something like this, which is pretty good. So when we run it on the test set, where again it's not seen this data before, we ask it to identify these bubble features. This is what it identifies, right? So blue is true positive, things that are genuinely feedback, what we want it to identify. The kind of purplish here is false positive, so it's incorrectly identified things. You can see this is happening mostly on the boundaries. And then false negative, which are things that are feedback that's missed, yeah.
Why are you using slices and not projection?
That's a good question. So here, what we're doing is I'm telling you results from the 2D algorithm. So what we do is we feed it slices in batches. So it sees multiple slices at the same time, but it's not really connecting information across slices. But ultimately, our data is 3D, so we're moving towards 3-dimensional identification.
So this was like tested out in 2D first before you moved on to 3D?
Yes, exactly. Yeah, so this paper is CASI 2D.
Oh, okay.
Yes, yes.
So here, what is it from false positives seem to be like part of the same structure? How do you decide if it's true or false?
We know the answer. We know the answer. Yeah, so here in our test set, we know where the feedback is. So this is pure simulation data. So we're training it on simulation data and testing it on data it hasn't seen before. So we know on a pixel by pixel basis where the feedback is supposed to be. And we basically identify that feedback in the same way in the training as we do in this validation.
Okay, so why is there something on the edge is not feedback, but the rest is feedback?
So you have to pick some limit in which something is feedback, right? So here we pick something like 1%. So when it falls below 1%, we say, all right, that's not feedback. But what I was about to say is actually that's pretty good, right? It's not identifying random cells elsewhere in the image. It's actually identifying something quite plausible, right? So seeing these false positives is actually, we're totally happy with that. I mean, it's pretty good. So yeah, but this gives you a sense of where our accuracy is coming from and how it's doing. Yeah.
Just to interpret these images, so
Yes.
do the same thing. It looks like the green and the blue and the purple all sort of overlap, but are they actually overlapping or are they separate?
Yeah, so I think some of this is projection effects. So let's see. No. So this is a pure slice. They're not really overlapping. They're just adjacent. And it's kind of the color
So
scheme.
in other words, it's only the things that look actually purple in the bottom ones that
Yes.
are false positive.
Yes.
The blue is true
Yes.
positive, and then the green is, it missed that.
Yes.
That's the false.
So part of the confusion, I think, is that the grayscale is adding structure
Yeah.
behind it. Yeah. So, yes, Phil.
If you have a hollow shell, but it's not a complete shell, for some reason you only have a segment of it, and you can imagine that the segment gets really small, that it just looks like a line. It doesn't look like an arc.
Yes, if it gets very thin.
When do you say it's not a shell, or you can't? Do you have a I can't tell category?
We have a confidence level. So what our algorithm is returning is a pixel by pixel confidence level. And so we, at the end, have to make a cutoff on what is high enough accuracy or not. So we are putting some cutoff on, so it is returning some likelihood, and we're basically applying a threshold at which we say, all right, this is the cutoff at which we believe the algorithm. Yeah. But in terms of structures, so some things are, very thin and look kind of like lines or shocks. But one of the things that the training is doing is we also include, false examples of where there's no feedback at all. So by doing that, we're trying to teach it the difference between shocks and the shocks associated with feedback. And what it's learning, these filters, is basically learning how connected patterns make up feedback. So that is partially an algorithmic thing, where you can choose filters that are 3 by 3, as we did, or 7 by 7, if you wanted to learn kind of larger features that are part of the structures you want it to identify. Yeah. Okay. So as you guys have pointed out, that was 2D. Real data is 3D. And this is particularly important with shells because shells are expanding. And so there is a connection across that third dimension. So we extended our algorithm to 3D. So now our filters are no longer 2D arrays. They're now 3D boxes. And it's learning connected structure in position, velocity, space. So we trained it again on the simulations. And now for the test, we apply it to the Taurus molecular cloud. All right. And we picked Taurus because Duo was actually a co-author on this Lee et al. Paper. So he was one of the people who did the original human identifications in Taurus, which is very convenient. All right. So here is what our 3D algorithm finds for previously identified shell TMB8. All right. So what you can see is that it's tracing around the inner part of the shell. And as you see it going through, this is actually, it is a horseshoe in 3-dimensional space. There's kind of it goes out this way where there's nothing. And so it's really tracking along the boundary of the shell. So why it picks, for example, this pixel and not, say, that pixel, this is part of the training, right? So it's picking up something after looking at literally thousands of these training images, and then using those same filters to identify structures in the real data. Now, here's the problem, right? So now, as soon as we moved into observational data, we again have the problem, how do you evaluate this performance, right? Again, we're now in a space where we don't have the ground truth. How do we know that our algorithm is working? All right. So here we go. So we evaluated a bunch of different hyperparameters, basically different models for the network. Here's each of those models applied on synthetic data. They all seem to do equally well on synthetic data. We also have one model that trains not on emission, but on the mass fraction of the wind. So in order to assess it, we have to assess it in the real data space. So what we did was we assembled a panel of 4 expert co-authors. And then we looked at, blindly, the data. And we looked at what the machine learning algorithm returned. And then we assessed each image independently on a scale of 1 to 5, where 5 we think visually is doing a good job, 1 where we think it's doing a terrible job. Right? So this is, in a sense, unfortunate because we're introducing some human bias into trying to pick the appropriate hyperparameters, but without the full ground truth, this is probably the best that we can do. So we did identify that some of the training sets and hyperparameters did better than others. These are probably pretty similarly good. So we picked our model emission 1 to use for our final analysis. Okay, so now I'm going to tell you the tale of 2 models. This best ME1 model and model MF, which trains on the mass fraction rather than the emission. Okay, so these are individual bubbles identified by human duo. And this is what the mass and momentum returned by our network is. And this is what he found by eye, trying to identify the shells from observations. Here's the 1-to-1 line. Model ME1 is doing fantastic, right, compared to what he did by eye. Yes, there's some scatter, but since neither the human nor duo knows the actual correct answer, this is actually pretty good agreement. What about model MF? It's predicting mass momentum that's lower by a factor of 10. So which to believe? So this is where we can return to the synthetic data and actually go back from emission to mass and see how well it's able to correctly predict the mass, right? So it predicted some shell structure on the basis of emission, take that emission, convert it back to mass, compare it to the true mass, which we do know because we have the simulation full information. So here's ME1. Here's the 1-to-1 line. So this is what it's supposed to be predicting from the synthetic data. And this is model MF. So what's going on? So what this is telling us is that ME1 is excellent at doing the things that humans do to identify feedback. Unfortunately, humans are biased because when you're looking just at emission, particularly in position velocity, a lot of non-feedback stuff gets mapped into those bubbles, into those shells that you're calling feedback. All right? So when you're looking at a velocity channel, you have some stuff that's truly feedback and some stuff that's cloud material. And so what's happening is, as humans and as model ME1, you can't distinguish that. But with model MF, we can train it to learn the underlying correct emission to mass conversion. All right? So if we know the underlying mass, we train it on that, and so what it's predicting is actually the mass fraction of the feedback at every voxel, not simply the confidence. So with this in hand, now we have our 2 models. We're fairly confident that we understand what ME1 is picking out. We think we understand model MF and what it's actually doing better than model ME1. So now instead of individual bubbles, we can apply it to the entire map, right? So the orange things were previously identified, and our map here is from the machine learning algorithm ME1, and it's integrated emission. So some of these things it's doing very well. The ones in red are high confidence, means it's been predicted by humans and also found by the machine. Model N1, these yellow, these are new things which seem quite plausible, like this thing over here, this thing over here, where there's sources here. They definitely look like feedback, like shells, but they weren't identified by humans. And then there's some areas where we don't think it's doing well. It's probably over-predicting, right? So some of this stuff here, where at least we can't find any sources. We can't guarantee that the source catalogs are complete, but if we have a couple different surveys and they haven't found a source, then it's probably there's no source there. Okay. But be that as it may, we can turn to finally doing some actual analysis. So we can now separate from our feedback maps the stuff that's actually feedback and the stuff that is not. So we can take the spatial power spectrum of the full map, excluding noise, and then only of the regions associated with feedback for ME1 and model MF, right, which we think is a true mass fraction. So we see there is a real trend. The spectrum flattens, which is what you'd expect if you were injecting energy on small scales. And this was predicted in the paper that I wrote in 2018 using just models. We can also look at principal component analysis. Here, this is a covariance matrix, so basically how correlated are spectra with one another as you go across the map. And you can see there's definitely changing between looking at the full map and looking at the feedback regions, right? In particular, we begin to see these structures that are developing when we're looking purely at the feedback. And so these seem to be associated with kind of coherent expansion, right? So bubbles that are expanding will have correlated spectra, and so we're beginning to see this enhancement in these maps that are, in principle, mainly feedback. And this was predicted in a 2016 paper, again, using synthetic models, right? So using pure models. So what about the takeaway points, right? What can we say about the mass, momentum, and energy of feedback? Right, here is ME1, 3,000 solar masses of feedback in Taurus. And here's model MF, only 300, a factor of 10 difference. Now this actually makes some sense because on the right, this new feedback mass in the shells is now finally comparable to what we think the stellar mass is, not 10 times larger. So considering that these are lower mass stars, that makes sense. Energy, 4 times 10 to the 46. All right, and for the ME1 is a bit lower. We think we're doing a better job at getting the velocity actually associated with the feedback features. It's a difference of 4. And both these numbers are very similar to what was found at human visual identification in the 2015 paper. Yes?
Is it saying that the observational papers that predict how much energy is being injected by a lens is off by a factor of 4?
That's right. Yeah, so mass and momentum are off, we think, by a factor of 10. Energy is off by a factor of a few. So, yeah, so this is our new model MF predicts much smaller values. Okay, so what does this say about the global evolution of the cloud? We often try to quantify this by comparing the dissipation of turbulent energy with the energy injection from the feedback. So it is a bit tricky. So how do you estimate the dissipation time scale? There's a formula from simulations of magnetized turbulence, which unfortunately I think depends a little bit on the numerics of the scheme that's being used, but it's pretty much the best we can do. For the kinetic energy, we have the bubble radius over the expansion velocity, gives you an effective time. So the value of turbulent dissipation is basically 2 solar luminosities. And model ME1 definitely suggests that, yes, feedback can offset the turbulent dissipation. But unfortunately, we think that this is an overestimate. So when we look at model MF, it's maybe a factor of 2 lower or more. So this can explain why previous estimates have found such large values. Hope is not lost. These are pretty uncertain ways to estimate it, but it does seem that the feedback is doing a lot less than you would infer just by looking at things by eye. So we can go to the humans versus machine scorecard. So winds create signatures in dust emission that we can identify by humans, and we can also identify using machine learning algorithms. So let's say it's 1-1. 3D convolutional neural networks can identify shells, so can humans, so it's 1-1. However, CNNs can learn hidden information and correct for observational limitations, including this line of sight bias where things get mapped into the same velocity channels. So humans 0, machines 1. So what we've learned from the post-processing is that there are statistics that are modified by feedback and are sensitive to feedback within regions. This spectral correlation function, this power spectrum, and the PCA covariance matrix. We think that to date, observations have overestimated the impact of feedback by maybe 4 to 10-ish. And so right now it's looking like this. The machines are winning. But I don't want to leave you on that note. So I'll go back to CASI 3D. We think this has a huge amount of potential. It can be used to identify protostellar outflows in the same way, which we're working on. You can probably identify supernova if it has the right training set. Filaments are cores. Again, if you have the right training set, you have to define what the filament and the core are first before you can use the algorithm, which is tricky. But you can use this to constrain observational biases together with the simulations, including radiation transfer and opacity effects and excitation temperature. And other CNNs are being used to infer physical properties, say, of the underlying turbulence. So provided you have the right training set, these are very powerful ways to basically reduce the dimensionality of the data and really extract out fundamental characteristics from it. And our algorithm is public and online. We submitted the paper on 3D, so hopefully we'll release that network soon. And so I encourage all of you to go and play around with this and see what applications you could find. Thank you.
Questions?
How large is your training set for bubbles? Like how many bubbles are in your training set?
For the 3D training set, I think, okay, so we're giving it something like 1,300 cubes, and those cubes may have different numbers of bubbles in them. So it's many more than 1,300 bubbles for a training set.
Sure.
Yeah.
So I was kind of surprised to learn that Taurus is full of bubbles for two reasons. One are the physics reasons that you suggested. There aren't any massive stars there. And secondly, because the density variations of Taurus are usually interpreted as filaments. Right? Nobody seems to have a big problem with a horseshoe-shaped filament. However, that doesn't mean that it's correct. Right? And then you say, okay, so now I'm going to go look for bubbles in Taurus, and it's pretty well known in science that you could go look for something and you might find it even if it doesn't exist. And then you're going to say there's all these papers, maybe more than 100, less than 10,000, talking about star formation filaments and critical mass to length ratio, and now you're saying no, it's not like that. It's bubbles and sequential star formation and Elmagren is Lada or something, right? So
I'm not saying sequential star formation. I didn't say that.
well, but you will be shortly, because that's what the bubble does, right? So I'm extrapolating.
Yeah, I'm not actually
right? And so
saying that.
how do you? And so the Milky Way plane is all full of bubbles. That seems fine. And then you come to Taurus. How do you know that you're even looking for the right thing? You train the set, and then you say, well, we have all these statistics, and you say, well, yeah, but it's not sequential star formation, it's filaments.
So first of all, Taurus is particularly interesting for another reason. It has an old population of stars that are 20 million years old. So this region, that's just been around for a long time. I'm not saying anything about triggering or sequential star formation, but it looks like Taurus has been percolating and producing stars for quite some time. So whether or not this is feedback, whatever it is not disrupting the cloud. It's not globally collapsing and forming stars at a really high rate. It's just kind of going along there. And so maybe that's consistent with the picture that these stars over time are producing some feedback impact, some feedback energy injection, but they're neither disrupting the cloud, but they're also enough to keep it from collapsing. So the feedback, I think, plays nicely with the story of long-term star formation because it provides one explanation for why the cloud is not globally collapsing. At the same time, it's not significant enough to actually trigger maybe a lot of star formation. But in terms of whether you believe it or not. So the humans who identify these shell structures really are looking at the 3D data. They're looking for coherent expansion. They see coherent expansion. The algorithm sees coherent expansion as well. That's what we're training it on. Certainly you can have false positives, but I don't think half of them even are false positives. I think it's pretty compelling if you look at the CO identifications in Taurus and you look at CO identifications in Perseus, you're looking at kind of the same things. So then that gets to back to the fundamental physics question is, what are these stars doing? How can low mass stars actually make these huge features? And so, I think this requires a lot more, a more careful look. My intuition for this is that if you have small clusters of stars, you can have protostellar outflows, that can clear some of the gas, so you don't have to do it with ionization or radiation pressure. So that's probably some of it, and then maybe the rest of it is once you make the gas more diffuse, you have your interstellar radiation field, right, also picking off some of the diffuse gases left in the center of the bubble, and maybe the outflow and whatever these combined effects are enough to actually push some of the gas away. But yeah, what the algorithm suggests is whatever is going on is not as significant as what you would get by eye, which in some sense is a little bit encouraging, I think.
I have a question that's not related to what Eric
Yes.
said, but just related to what Eric said. Did you try this on a simulation that had no bubbles in it?
Yes.
Just filaments, to put Eric's way.
So so in CATC 2D, definitely we have bubbles, snapshots without any bubbles that are part of the testing set, and it doesn't identify things.
Does that make you feel better?
No, my question is more like, should you really believe an observation without a theory or something?
Oh, that's too philosophical. Let me ask you
ITC Colloquium.
Well, my other question is somewhat theoretical.
Okay,
so
good. Yes,
okay. So Hector and I always have this problem, and I think you and I have had this discussion too, that you get a snapshot of all this, and so like you had this kinetic time, right, of the size over the current velocity, and so that's a current size and a current velocity and a current luminosity as a result, right? So how do you account, I mean, you could in simulations, maybe you do, but for the history of this whole thing, and like to go back to Taurus, that's a long history.
Yeah. So we have different times in the training set, but that mostly impacts different expansion velocities, different sizes of bubbles. As you say, for Taurus and Perseus, what we're getting out is just a current snapshot. You really can't say anything about the history at this point because it's really hard to estimate those timescales and what the bubbles were doing in the past. Maybe with some more detailed modeling in comparison of specific bubbles you could, but that hasn't been something I've really thought about.
Because the turbulent dissipation time has the same problem.
Yes, right, it changes over time probably. Yeah.
Next.
If I understood you right, you're judging the effect of bubbles, or things that produce bubbles, on the amount of turbulence that is produced because the bubbles interact with the magnetic field lines and alpha waves propagate out and make things look turbulent. But does that mean that you did not include individual young stars which make outflows but not necessarily show up as bubbles?
So one of the things that we found when running the network on the observational data is that sometimes it will identify outflows. Outflows are coherent velocity expansion over many channels, so it makes sense that it does that. But of course it doesn't do so perfectly, which is the next part of the project, which is to actually simulate the outflows.
Because there are, I think, when you have more massive stars or clusters of stars, then you tend to get things that could be called bubbles. But when you have lower mass stars that aren't necessarily all in clusters, maybe they're just sprinkled out through the filaments of the region, you're not going to see bubbles, but they're going to contribute to the turbulence because their winds are going to impinge on the fields just the same way as the shells do.
So I would imagine that you're going to have a significant contribution to the total turbulence from individual low mass stars that might be comparable or even bigger because low mass stars are so numerous.
Now, for the outflows, this is something that Alyssa estimated in her paper, and they also did in Lee et al. The outflows, if you identify them and count up their mass and infinite energy, generally less than what you get from the shell-type structures, by a factor of, I would say, 5 to 10 even, something like that. So
Who knows, maybe we have misidentified those too. Maybe you have to do this for bipolar outflows.
we'll find out. So
5 to 10 based on observational estimates.
observational estimates,
then-
yeah.
If you take that into what you find into account, wouldn't that,
Lower it some more.
I mean, not lower it some more, but let's just say hypothetically, with the outflows, you don't see this effect that you see with the winds, where you lower the energy momentum from a factor of 8 to 10. So then wouldn't that kind of put that at about the same?
It's hard to say. My sense is that people have been more careful about modeling and correcting factors for outflows than they have for the shells.
Yeah.
Just because they're easier to model. And
Yeah, I guess
the winds have been very perplexing because it's hard to even figure out how they would get that much energy to create this expansion, which means that it's hard to constrain the biases there. So I'm a bit more positive and confident about the observational outflow identifications because people looked at very high resolution data from the outflows and can really get a sense with models for how to make these corrections. But this is something that we'll look at.
Oh, put it on par. I mean, it would like make them, if it doesn't change, if your analysis doesn't change, then it would say that the energy momentum in the bubble is the same in the outflow.
Probably still a little bit more, but yeah, closer to comparable. Yeah.
Anna?
So I was wondering whether the whole census of bubbles that you are identifying with machine learning can help you answer some of the questions that have been brought up, such as like the time dependence or like the influence of like different mass stars, and whether the sample you're finding is kind of unbiased enough to kind of allow these sort of population studies of bubbles.
Yeah, so one offshoot project would be to look at the bubble properties and then the stars that are nearby and try to make some physical connections. We haven't done that, but I think in Taurus, there have been a couple of recent surveys across it all. 2017 one, they really mapped the entire thing to try and make sure they had as many as possible. So they have, as far as we know, a very complete set of stars from, say, the other surveys, class 1 to class 3. And so I think you could begin to answer some of those questions, particularly with the help of guided data, making sure that you have things, you have the correct things within the cloud. With Perseus, this has been, so there's another project with faculty in Texas where they were going to follow up on many of these B-type stars and really get better spectral typing for them, and that would be extremely helpful because then we could begin to constrain their properties. If we have much better spectral types and masses, then that would help a lot too.
So it's 12 o'clock, so we'll leave it at that. Thanks, Stella, again.
Yes.